Lab 2 on charged tapes. In this lab, our goal is to make a more accurate estimation of the electric charge between two charged U-tapes. Multiple charges are modeled on each tape as opposed to treating the entire tape as a single point charge like how we did in the previous lab, using the same floating tape model that we had in Lab 1. Some of the concepts that we cover in this lab include point charges, electric fields, electric forces, and Coulomb's law, for which the formulas are shown, and Newton's second law, also known as the momentum principle, as well as superposition. In Lab 1, we find the amount of charge on one U-tape, which is the top tape as shown in the diagram to the right, tape B, with the vector forces shown on it. We made a couple of assumptions. We assumed that the U-tapes have the same net charge, we treated each tape as a point charge, and we also ignored air resistance. We got that the measured separation distance between the floating tapes in the model, in the model that we set up, was 0.038 meters, and using that, we calculated that the gravitational force, and we also got that the gravitational force was 0.00196 newtons. Plugging in values and solving for Q, which was the charge on tape B in Lab 1, we got a value of 1.773 times 10 to the negative 8th coulombs. This is some more data that we obtained from Lab 1 in order to calculate things like the the magnitude of the gravitational force and the electric force. We needed the length of a piece of tape and the approximate mass of one piece of tape, that's 20 centimeters. And this is the computational model output from Lab 1, and as it can be seen, there's only three vectors shown, the green arrow being the electric field force on the bottom tape due to the top tape. The yellow arrow is the gravitational force pulling down the top tape, and the orange arrow is the electric field force on the bottom tape pushing the top tape up. We modeled everything as having single point charges in the center of the tapes rather than how we're modeling it in this lab, which is a line of multiple point charges on the top tape and the bottom tape. And this is the computational model output for the code from Lab 2, in which it can be seen there's the it can be seen that there's there's a line of charges on the top and bottom tape, and the yellow arrow is the gravitational force going downwards, white arrow is the electric field force going up, and there's also green arrows shown for the electric field forces at the charges. And in order to get the magnitude of the electric field force, or the electric force and the gravitational force shown in the text output to be approximately almost the same as each other, I did a guess and check to obtain the estimated charge for Lab 2 value shown on the right, which is 1.857 times 10 to the negative 8th coulombs. For comparison, in Lab 1, the value that we got was 1.773 times 10 to the negative 8th coulombs for the charge on tape B, tape B being the top tape. So for the coding in Lab 2, the function shown in the bottom left is calculating a single electric field at a point. This function is repeatedly run for multiple iterations in a for loop later in the code in order to get multiple electric field values for the next part of the code. And in the for loop shown right here, the electric fields are summed with this loop to calculate the net electric field. The magnitude of the charge on one piece of tape from this computational model, as shown earlier, is 1.857 times 10 to the negative 8th coulombs. The reason for why the estimations differ between Lab 1 and Lab 2, and why the value from this lab is likely to be more close to the real value, is that we only accounted for the electric force in a single direction in the model that we created in Lab 1, which is just the y component of the vector. So the value for this lab, 1.857 times 10 to the negative 8th coulombs, should be more accurate because it accounts for the electric field forces for multiple charges that also have components acting in the x and the y directions.